Luc Nguyen from the University of Oxford that will talk about minimizing the Ginzburg-Landau energy, and it's going to be a board presentation. Thank you.
Thank you for the introduction, and I'd like to thank the organizer for inviting me here this time as well as the last two times, I suppose. In 2019 and probably another time, a long time ago, I don't remember what it was. It's always a pleasure to be back here. Okay, so I'm going to talk about some recent joint work with Amadei and Natalio. So I will look at this functional. So I would call it F of U. So this is on some domain omega, and I would just take the one that many of you are familiar with, 1 minus u square dx, where here u will be a function from omega into a complex plane, but I'm a real person, so instead of working with C, I work with R2. And omega is sitting on either 2-dimensional or 3-dimensional. So just to fix idea, omega are going to be either this. So this is a slab of with 2D and 2D or 3D. Yeah? Or I could look at a ball. I look at a disk of. So this is a ball of radius d. This is a cylinder in R3, and this is the x-axis. Yeah? Maybe this is the x. Okay. Maybe I call this the x1. So what I'm interested in is the critical point of this function. So they would satisfy the equation is minus Laplacian of u is 1 minus u squared u. So this is on that omega. And on the lateral side, I will impose Neumann conditions. So this is the u0. So they're free. And at infinity, I will impose that u x will tend to minus plus 1, 0, 1, as x1 tend to plus minus infinity. So basically, on this end here, I want my map u to point this way, and at this end here, I want to point down this way. So this model come up in a number of physical contexts. So today we've seen a lot about liquid crystals. It show up in the model Ginzburg-Landau for liquid crystal, but the context I'm describing today is in the context of Bose-Einstein condensate. So your u is your wave function. So for now, to give a physical motivation, I will describe the 3D picture, but when I start talking mathematics, it will be entirely 2D, because the set of things that we get there is a lot more complete. Whatever that I say mathematically in 2D has a 3D version, but it's just more cumbersome to state. Okay. So here there's a series of papers published in all of them in Physical Review Letter throughout 1999 all the way to 2014 by several group of people. So there's Berger and company. They're quite long names, so I don't think I have all the names in my head. I just list the first one or the one that I know. Nadello and there was So they are experimental paper, but there was a lot of confusion. So let me describe the experiment that they did. So in this context, one particular solution, so is given by in closed form. So I call it so this is the soliton. So it has the closed form x1, or just x. So this is minus tangent hyperbolic of x1 divided by root 2 and e2. So it's a one-dimensional solution. So what they do the experiment is like this. Okay, so they look in a strip, not on a strip, on a cylinder. Then what they do is that they put they put the solid this condition, they treat it, so they put it on the cylinder, and then let it evolve by the nonlinear Schrodinger equation. So initially the molecule align like the wave function align like this. Here it's entirely zero. So here the u is zero here, and then on this side here it goes down that way. Okay? So at every line on this strip it looked like that. So they changed the width of the band, and they observe what happened. In the at the beginning, they see this picture staying there for a long time, so they're not going. So they let this and they perturb a little bit and then let it evolve. So they see this picture, so they thought that they observed what is called a soliton. A few years later, somebody else tried some of the experiment, and what they see is that after some time, it evolved. So here it's still like this, but on the center plane, what they see is that the zero set is no longer this thing here, but it's only it's a circle. And everywhere is non-zero. So they thought that this is what they call the solitonic. They call this the vortex ring. And then they stopped there. And a few years later, somebody else actually ran it a little bit further and see that actually it doesn't stay there. So what it will happen is that a few moments later, well, a few could be very long. So what it's gonna do is that that circle there, it's gonna move a little bit down. It moves a little bit down, and at some point, it's gonna open up like that. And then eventually, what it settles down to is a solution that looks like this. It's a straight line. So the zero set becomes a straight line, and what they now call this is the solitonic vortex. So that is the physical thing happened in that 15 years of progress. And this thing here was done for a number of material. It was for, this is for both bosonic as well as fermionic. So it all happened in all of that. So what my talk is about is to somehow understand this in a mathematical way. So somehow I want to see some kind of energetic structure of these. Yeah. So what I want you to keep in mind is that you start with the soliton, then you evolve for some time, you're going to see the vortex ring. You evolve for some of the time, you're going to see this solitonic vortex, and it's going to stay there. So from the sound of it, that in terms of what we call, so this would be unstable, this is metastable, and this would be the stable one. Yeah. But all of that is wrong, we see in a minute.
Excuse me, for understanding, can you add the arrows around the
Yeah.
lassos?
So that very good. So the arrow gonna go this way. This is gonna go this way, and this is still going this way. And this guy here inside here is gonna go that way.
Yeah. And at the bottom?
So at the bottom it go this way and it goes this way.
Sorry, and the evolution is by gradient flow? Or?
It's the NLS, the nonlinear Schrodinger.
Okay, the Schrodinger flow.
Yeah.
Okay.
Of course, when you do NLS, there's also another class of solution that called traveling wave that you might care about. So these are traveling wave with speed 0. So I'm not looking at the other one are more difficult to look at mathematically. So maybe for traveling wave, so I would only refer to the paper by Helaine, Sandier, and Smets. So I'm not going to talk about it at all. So what I talk about are just steady state. So these are physical experiments, and from a numerical point of view, there's a few papers by numerics by Braun and Reinhardt. So this is physical review I, so O2. Then Matteo and Braun. So this is GIL 14. And there's also this is GIL 02 as well. Yeah. So they, physically they observe all of this thing here, and numerically they observe all of these pictures. They explain this by what is called so the explanation. So they call it snaking instability of the soliton. Okay. So what I will do now is that I will talk about the mathematics of this. So how are we going to see all of this using variational method? So first remark is that this is a really simple remark. That the infimum over a space that I will describe in a little bit. So this is suitable space of this function of fu is actually 0 and not a plane. So the space that we're going to look at is that there are many different ways one can do this, but I think in this talk here we're going to look at the space. I'm going to put here is you take the solitonic vortex and you add h1 of the omega. Okay, so that's one thing, and of course this will not explain any of that. The second thing, which is bad news for variational method, is because the domain is infinite, is that something that called the Pallas-Moe condition is false. So that's bad news for minimization. So basically, you take a minimizing sequence, or even taking a sequence of admissible map converging to a critical energy. That sequence doesn't converge woodly anywhere. So. Okay, so then that means that in order to minimize or to apply variational method, we have to introduce something. So there's two symmetry that has been used or imposed on this thing here to force the existence of a solution. So two symmetry assumption. So one assumption is rather on physical ground, so they call it phase imprinting. So basically, in running the experiment, what the physicists do is that they impose that the wave function on this end and on this end are somehow conjugate to one another. Okay, so that means that if you look at U1, so this is an even in x1, and U2 is odd in x1. Okay. And from a physical point of view, that is not too that's not too bad. Somehow physicists like it. The second assumption, so this is a physical condition. So there's another condition that mathematicians has been using, which is not physical, and physicists, all physicists don't like it. It's called imparity. So basically, this is an ad hoc condition to force. So this is an ad hoc forcing that U1 will have to be 0 on the center of omega. Yeah. So basically, that imperative will force the admissible map to be 0 here. U1 is 0 here. And so more precisely, what they do is that maybe now, how about now we're talking only in 2D. Yeah? Then quicker, easier to draw. So there's only two axes. So this is x1 and this is x2. So then u1 would then be odd in x2, and u2 is even in x2. So say, for example, that's one way of forcing that constraint. So by doing that, use the theorem. So theorem. So this is Abtalion and Sonier. This is 23. Is that there exists a minimizer in the class of admissible symmetric configuration. And furthermore, there's two things that they do a number of other things, but maybe I just put down the two things that are most related to what we're going to do. Is that for D, so D is, remember, D is the thickness of the strip. So if D is very small, then the minimizer is the soliton. and for D very large, then the minimizer is something else. It's not the soliton. So what it's going to look like is this. So in the 2D picture, for D very large, then so if we put in the arrow we're going to go this way here. So exactly at this thing here, we're going to have something that go like this. So it has a vortex structure. Yeah. So vortex here, and because it's look like in the far field look like a soliton, so people call this the solitonic vortex.
Excuse me, that is the very narrow case. D much less than 1.
This is D much bigger than 1.
Oh, okay.
Yeah. D less than 1, it's just the one-dimensional solution.
What boundary condition do you have?
So the boundary on here is just Neumann, and here it's just the plus minus 1 at infinity. So this is slightly different from something you're going to hear on Wednesday when at infinity it's going to be Neumann and or decay, and on the lateral boundary it's going to be a vortex boundary. So you're going to see that on Wednesday in Radu's talk. Okay, so this kind of explains something here. So I mean, if I'm going to repeat, suppose that somehow I can impose imparity in my physical experiment. I rerun this experiment. Initially, I start with the soliton. The soliton is not minimizing, so the numerical thing, we know that this is unstable. So if you perturb it a little bit, it will not stay there. So we'll try to go to a minimizer. And the minimizing one is here. So it will be the solitonic vortex. But it doesn't explain whether you're going to see the vortex ring or not. Okay? So okay, so then so after they this work, then they also do a bifurcation. So this is another theorem by those two and another one. Breakjar and Sandier. So this is, I think it's last year. So, so at D is equal to K pi root 2 over 2. So where K is an integer, right, so K is 1, 2, etc. So the soliton bifurcate to two local branch of critical point. So the most relevant one for in understanding that picture is that if when the width here is bigger or equal than so K is equal to 2, so 2, so it's pi root 2. So at that width, what they observe is that it's going to split. It will want to split the domain into 2 halves. So it's going to introduce 2 vortex here. So one of degree 1 and one of degree minus 1. And so this one here, if you think about it, so this is a 2-dimensional picture. So introducing a point here and a point here would look like a sphere of dimension 0, right? So basically, that's the 2-dimensional analog of the vortex ring. Yeah? So this is this is vortex, anti-vortex. So this is the 2D vortex ring. Okay, but we know that in this case here, right, so there is a competing one is the solitonic vortex. So what we like to understand is that okay, which one has higher energy and which one has smaller energy. And if we believe in physics, then we would think that this is has higher energy and that one would have the smallest energy, right? And at least for D bigger than this width, we have that. So what my theorem says is that, yeah, we do answer all of that. So this go back to something that I did a long time ago, perhaps around the time that I came here some 6 years ago with, so that's some joint work with Agir and Val and Radu. So I have maybe it's time to then I state a theorem and then this is so it's finishing up. So so if 0 is less than D and less than or equal than I root 2 over 2, then the minimizer or the symmetric minimizer here is the soliton. So now instead of saying that for D smaller than 1, we have precise number. And if D is strictly bigger than that number, then the minimizer looks like the solitonic vortex. So actually they are exactly a true minimizer. So and they look like the solitonic vortex. So one with degree 1 and one with degree -1. So one gonna go this way, and the other one has the opposite one. So, now I'm a bit confused how to draw the other picture. Yeah, one go. Yeah, I think one has degree 1 and one has degree -1. Basically, it's just a flip in the sign of U1, right? So this one here is U1, U2, and this is -U1, U2. Actually, yeah, okay, very good. So these things are saying the same, but when I'm going down here, then one would like to go that way, and in here, so we want to turn.
You should throw the river the top horizontal and bottom horizontal. Just make the opposite directions.
In here. The U1, yeah, U2 stay the same, U1 flip, yeah. Okay. So this will give you a clear picture of what happened with the first theorem there. But what is it that we have to say about here? So what we do here is that if we introduce more symmetry, so here you can think about this as having imparity is nothing to say that it has a symmetry with respect to reflection around this axis. Okay. So now what you're going to do is that you can, instead of putting here, so you can decide that, okay, I'm going to split this into a different band. And in each of these bands, I have this midline here. Right? And then I can impose symmetry around all of these middle lines. So then in here, if you have K band, then you introduce ZK, Z2K symmetry. So to avoid technicality, I will not define for you specifically what it is, but you can think about, so U1 would be even around the solid line and odd around the dashed line, and U2 would be even around all of those lines. Yeah. So then in here, you would say that so the theorem is that if D is less than K pi root 2 over 2, then minimizer is the soliton. And if D is bigger than that, then K pi root 2 over 2, then minimizer will have K plus or minus 1 vortices. So the vortices will be introduced exactly at this point, and one configuration is plus 1 minus 1 plus 1 like this. So the sign is going to get alternate. The total degree is 1. Okay. So what a consequence, a corollary of this that you can prove out of that? It's simple, but somewhat technical to write out explicitly. But the energy of so the vortex, anti-vortex, will have energy bigger, right? So it has higher energy. And the vortex. Yeah. So basically, we completely explain this picture if we're happy to impose symmetry. So I have around 10 minutes. So what I'd like to talk about now is what we do with our imparity condition. So we will keep the imprinting because that's what physics tell us that we should just keep. The question is, what can we say without imparity? So question. Or how to understand this. Without imposing the imparity condition. So you can think of imparity because of the even and oddness assumption. It will force a number of zeros somewhere. So imparity is just a way of forcing a zero to come up. Yeah. So imparity is existence of zero, or imply existence of zero. In the context of these things, we know that there's another way to force the appearance of a zero is a topological degree somehow. So what we're going to do is that we do a homotopy, and if we have two maps sitting in different homotopy, and I'm trying to connect them, I will have to induce a singular somewhere, right? So that would be that thing. So a different way of imposing 0 is that different, so path between different homotopy classes. So even though the minimizer doesn't exist, we can look at approximate minimizer and see how it looked like. Right, so I look at a sequence of FUM and tending to 0. I want to see what UM look like. This guy here will have integral of nabla UM square right. I know that this is going to 0. So let's be a bit naive and let's say that, okay, I would just make modulus of UM is 1. So then that would be gone. Can I make this happen? And of course you can. Right, so in this case here, so let's say that we make this is 1. Then you can write UM in this form. So cosine of psi m and sine of psi m. Right. And you calculate the norm of UM is going to be the gradient of psi m squared. Right. So in order to make this going to 0, basically you just make the gradient of psi very small. Psi is a scalar function. So basically psi m looks something like right. So basically you can just do it something like this. You take a function psi and you divide by m like this. Well, psi will have this shape. So that's minus pi over 2, and psi is something that looks like that. Yeah, so the odd function like that. How do you do that? Take any function psi, then you just rescale it in the domain variable, and so that will do it. So basically, you look like, okay, that's one way of doing it. But then you can also do it by changing, like I said earlier, you can just put the plus minus sign here. That doesn't change anything. Right? So now, what you have is that if you look at the image, so this is U1 and U2, then on 1, right, so at infinity, so now if you look in the x1 axis, at infinity will correspond to those 2 points. And if you go along the plus side, then your map gonna sit on this part. So that's the plus part. And if I do, if I use the -1, then it's gonna stay on here. Yeah. So in a way that these two maps live on different homotopy of map connecting this to this, because you cannot continuously form this blue curve into a red curve, making sure that it stays on the circle. Right? And there are other paths you could take. For example, you can just loop around it once, or loop around it more. Okay. Okay. So then, what we do with 5 minutes left, I will.
Sorry, before you mark that, I'm trying to imagine, as you go further to infinity,
yeah,
you still need the circulation to go around, right?
Yeah.
Doesn't that give you a big gradient in the wider in the vertical direction? And the energy is finite, you tell yourself.
Yes, the energy is finite. Yeah.
It's not surprising.
Yeah, it decays exponentially to
right.
plus and minus 1.
Like
So,
the tangent.
like at infinity it looked like the tangent hyperbolic.
Okay.
Okay, so then I look at, I fix some very large ends, yeah. Then I look into that, this gamma is this is the set of all map, H going from -1, 1 into US plus H1 of omega, such that H is -1 or ±1 are those maps. So let's call this plus minus, yeah? So this is U plus minus M. Okay. Then if you know what I'm doing, then I'm doing the mountain pass energy. So I look at the mountain pass energy. So I look at this guy here, which is equal to the infimum over all path in gamma, and I take the supremum over the energy of H of T. Okay, so this is T in -1, 1. Okay. So basically, I'm sitting, well, I don't have a minimum, but I have 2 points that are almost like zero energy, and I'm trying to go from one to the other one. Of course, if I'm staying on a unit sphere, on the unit circle, I will have a problem. I cannot do that. But now we look at mapping to R2, so we can do that, and then it will force a zero to appear somewhere. Okay. So then the question is, what is this energy? Then what we so there's a theorem that if D is less than pi root 2 over 2, then C is just the energy of the soliton. And if D is bigger than pi root 2 over 2, then what at the moment all we can say is that this mountain pass energy is at most the energy of the vortex. Okay, so we don't have a full answer, but and there exists a D star bigger than pi root 2 over 2, such that C is actually the energy of the vortex for pi root 2 over 2 less than D less than that D star. Okay. So I know that if I go a little bit, the width go a little bit beyond that critical threshold, then I do see the vortex at the mountain pass level. Of course, we would conjecture that that D star is infinity, but we don't know how to get it yet. And I think I have 1 minute, but I would rather stop there. Thank you very much.
Thank you very much. That was wonderful talk. Some time for questions, and then we continue with the research.
Why was the minimum not changed?
Yeah, so for example, we can take something like this, that would have the energy. So if this energy is 0, then this has to be 0, and this will have to be 0. But then if this is 0, then it cannot be plus and minus 1 at infinity. Yeah.
Still trying to, the asymptotic of this vortex, is it up and down?
Yeah.
Across the entire strip at some point, including at the boundary?
Well, at infinity, yes. Yeah. So basically, you can think of it like this. You put a vortex only near the origin here, then somehow you interpolate it at far side. It's just basically the soliton. So that's why we call it the solitonic vortex. You know, you look far away, it looks like the soliton, but you look closer to the core, it's not.
Okay, maybe if we continue outside, so we are almost in perfect time. Thank you very much.